Welcome to Gooseberry Science and Education videos. My name is Noah. And together with my little orange gooseberry assistant here, we're going to dive into the fascinating physics of your kitchen counter. We use this appliance literally every single day, but how many of us actually know the incredible science happening right behind that glass door?
So the big question we all ask when we toss in our leftovers and hit start is this: how does this magic box actually cook food so incredibly fast without any fire, glowing coils, or, well, any obvious heat source? It feels like magic, but it is pure, brilliant physics. In this explainer, we're going to cover a happy kitchen accident, how the magnetron works, the physics of heating food, solving the cold spot problem, keeping the radiation inside, and finally, getting some major health myths debunked.
Part 1, a happy kitchen accident. Let's step back in time to the 1940s to discover how a military technology accidentally changed home cooking forever. American engineer Percy Spencer was working on radar magnetrons when he noticed something really unusual. He was standing right near the active radar equipment when he suddenly felt a chocolate bar melting in his pocket. He quickly realized the microwaves from the radar were generating that heat. That happy kitchen accident led to some popcorn experiments and ultimately his brilliant patent of the microwave oven in the 1950s.
Part 2, how the magnetron works. To understand how Percy Spencer cooked that accidental chocolate, we need to look at the most complex physics concept hidden inside the machine, the magnetron. Now, it sounds totally intimidating, but just think of the magnetron as a mashup of two really common things. It fires electrons in a vacuum, much like an old television tube. But instead of hitting a screen to make a picture, it uses resonant cavities to create invisible waves, exactly like someone blowing air over the open holes of a flute to create sound waves. This brilliantly illustrates the inside of that magnetron. Notice how electrons literally boil off that orange central cathode when it's heated. But instead of flying in a straight line, powerful magnets force them to spin outward in this curved cycloidal path. As they zip past those circular resonant cavities in the anode, they pass their energy to the cavities, making them resonate and produce microwaves at exactly 2.45 gigahertz. But those newly born microwaves can't just hang out in the magnetron. They travel from there through a metal funnel called a waveguide. The waveguide perfectly channels them, bouncing them off the metal walls right into the main cooking compartment where your food is waiting.
Part 3, the physics of heating food. The crucial point here is understanding what happens when those 12-centimeter waves actually hit your bowl of soup. How does a wave become heat? Well, it all comes down to a process called dielectric relaxation. Microwaves create a rapidly changing electric field, and water molecules inside your food are dipolar. They have a positive and a negative end. The microwaves force these water molecules to frantically flip back and forth billions of times a second, just trying to align with that changing field. Because they constantly lag behind just a bit, this frantic microscopic movement generates intense friction, and that friction is exactly what creates the heat.
Which brings us to, honestly, one of the biggest kitchen questions out there. Do microwaves actually cook your food from the inside out? The answer is a definitive no. Actually, scratch that inside-out idea entirely. Microwaves lose their energy very quickly when they hit the moisture in your food, penetrating only about 1 inch deep. That means the deeper interior of your food actually cooks from the outside in via thermal conduction from those hot outer layers. This is exactly why your microwave meals always tell you to let the food stand for a minute. It gives time for the heat to conduct fully to the center.
Part 4, solving the cold spot problem.
Have you ever wondered why your microwave has a rotating glass plate inside? It isn't just to give your leftovers a scenic ride. This thermal imaging provides undeniable visual proof of what happens inside the cooking chamber. The microwaves bounce off the metallic walls, forming what are called standing waves. This creates distinct hot spots and completely cold spots. And that is exactly why the turntable is absolutely necessary. It constantly moves your food through those invisible hot and cold zones to ensure even heating.
Part 5, keeping the radiation inside.
Now that we know exactly how it heats your food, let's talk about the brilliant engineering that keeps those exact same waves from escaping the door and, well, heating you. The physics of the door comes down entirely to scale. The microwaves cooking your dinner are roughly 12 centimeters long, but if you look closely at the mesh screen on your microwave door, the holes are only 1 to 2 millimeters wide. The microwaves are physically way too large to fit through those tiny holes. This incredibly simple but effective design creates what physicists call a Faraday cage. Visible light, which has a microscopic wavelength, can easily pass right through the holes so you can see your food spinning. But the long 12-centimeter microwaves hit the metal mesh and bounce safely back into the oven.
They simply cannot pass through gaps smaller than their own wavelength. Between that Faraday cage mesh door, specialized choke flanges engineered into the door edges to reflect stray waves, and instantaneous safety interlocks that cut the power the absolute millisecond the door is pulled open, your microwave is incredibly safe. The leakage is far, far below the strict FDA safety limit of 5 milliwatts per square centimeter.
Part 6. Health Myths Finally Debunked.
Since we know for a fact it's safe to stand next to, let's bust the final myths about what the microwave is supposedly doing to the chemistry of the food itself. Some worry that microwaving makes food dangerous or radioactive, but the math tells a totally different story. Microwave photons have an energy of roughly 10 to the -5th electron volts. That is millions of times too weak to break chemical bonds, create dangerous free radicals, or alter the food's molecular structure in any harmful way. It is literally impossible chemistry. In fact, Harvard Health explicitly backs this up. Dr. Anthony Komaroff notes that because microwaving takes less time and uses less water, it actually prevents nutrient breakdown much better than traditional cooking methods. Yes, it can actually be nutritionally advantageous. By cooking rapidly and avoiding the large vats of water used in boiling, microwaving is essentially the ultimate way to keep your vegetables packed with healthy vitamins. When you boil broccoli, the nutrients leach right out into the water that you just pour down the drain. The microwave keeps those nutrients right where they belong, inside your food.
So, did you realize you conduct a 2.45 gigahertz quantum physics experiment inside a Faraday cage every single time you reheat leftovers? It makes you wonder, what other incredible quantum physics experiments are hiding in plain sight in your home? Please like and subscribe if you enjoy the content. We are already working on a new topic.